Make sure you get that second one right away. Good point there.
You can have my second one.
Already done it.
Oh, well then.
Somewhere around page 100, I think.
It's page 99.
99. Thank
Yeah.
you. Let me get that. Sorry about that. All right. So page 99, friction. All right, and let's just start with this here. Let me just go this way a little bit. Actually, let's do this. All right. So we're looking at two blocks here. I'm just going to use two objects and try and explain why friction is such a tricky topic and why you got to give it your attention. So right here, we're looking at this. Oh, let's use this. So we have two blocks, a book and some Kim wipes here. And one of the things that's tricky about friction is there's different types of friction. There's static friction, there's kinetic friction, there's even a thing called rolling friction, which we're not going to focus too much on. And what's very unusual is the term static and kinetic friction. Usually when you hear those, you think of static as something at rest. Well, okay, so you might think static friction applies to objects which are at rest. Okay, however, even in this simple example, where I'm moving this book back and forth, we see that this box of Kim wipes here, if I move it slowly enough, is not moving relative to the upper block. So it is moving, but it's not moving relative to the object that it's sitting on. In this case, static friction is actually what's keeping this moving block in motion. Very confusing, right? There's a number of different cases. You can see if I hit this hard enough, it starts to slide relative to the upper block. And this is pretty crazy. In fact, the directions of friction in this problem can get somewhat confusing. Now, I want you to look at this very carefully. I'll put this right here at the edge. And I want you to watch this upper box. In particular, I want you to see which way it moves when I hit it relative to this bottle. Oops, let me hit a little bit harder here. Let's go right here, right here. Ready? Which way did the box on top move relative to the bottle? Point with your hand. Really? Look at it. Right now, it's lined up with the bottle, right? Watch the box carefully. Is it still lined up with the bottle? No. Which force caused the box to move forwards? Friction. Right? Do you agree that this is going to take a little bit of effort to get this right? It's counterintuitive. Now, to be clear, which way did the box move relative to the book? Yeah, so it moved relative to the book backwards, which is why friction was forwards, which is why the box went forwards. Woo! Okay, let's put some notes on the board and try and understand this. That's really, in a nutshell, why physics is so tough. All right, or at least frictional forces. All right, so we've got a bunch of notes on page 99. You can read those or you can kind of watch me here, whatever's working for you. Friction is a tricky force. The symbol we're going to use is lowercase f. To be clear, lowercase f is not a vector, but technically this is the magnitude of frictional force. We know the units of force in general. What are the units for friction? Say again, sorry. Newtons. Yep. We got newtons. All right. If you want, remember our old friend mg. It's a kilogram meter per second squared, if that helps. The units of m times the units of g, if that helps. Now, and I want to make sure I'm doing this. You heard me say this a couple of times. I was talking about surfaces and relative motion. If you have surfaces in relative motion, friction is an easy, it's almost fun. Friction is fun with an extra line. If you are not used to this symbol, this is the Greek letter mu. If you don't know how to draw it, draw a letter U and then just draw an extra line down. Okay? Draw a letter U, draw an extra line down. It's not an M, it's a Greek letter M. All right? Notice the subscript K. We're going to call this mu kinetic. Mu subscript K means mu kinetic. What is N? Okay, strictly speaking, do you agree in this case it's not normal force, but normal force? Yep, you know what I'm saying? So far, so good. So we have to be a little bit careful here, right? Friction does not point the same way as a normal force. In particular, think about those blocks we were just looking at. Friction was parallel to the table, whereas normal force was perpendicular to it. In general, normal forces and frictional forces are perpendicular. So we could use this equation if we use magnitude, but not if we use vectors. It doesn't make sense. Okay. Sometimes mu kinetic is called the kinetic coefficient of friction. And I want to underline coefficient. I want to talk about the units really quick. In this case, what are the units of F? Newtons. What are the units of N? So what units are left for mu? Mu has no units. Now, a pet peeve of physics teachers everywhere is when students call G gravity. That's just not right. Another pet peeve is when people say mu is friction. That's not right either. Clearly, G relates to gravity. Clearly, mu relates to friction, but mu is called a frictional coefficient. Everybody got that? If you write a free body diagram and you draw mu as the force, you get it wrong. All right, so let's not do that. Just watch out for this. It's very easy to slip into that trap calling G gravity, not true. Mu friction, not true. Good enough on that? Just trying to make sure you speak clearly so when you transfer, you don't look stupid. All right, number 2. That's the easy case. Okay, if the surfaces are in relative motion, easy. We've got this formula. We can learn all about it. If the surfaces are not in relative motion, I think I put this in 2 cases, and let me make sure I get the cases in the right order. You'll see these words in physics problems sometimes. A block is on the verge of slipping. If you're not sure what that means, I'll show you an example with our friendly Kim wipes. Right? Right now, do you agree this block is not on the verge of slipping? But as I tip it, at some point, oh, it's just about to slip right about at this angle. Well, it's even there. So right about at this angle, it's on the verge of slipping. Oh, geez, sometimes it even is slipping. So a lot of problems will talk about this moment just before slipping. So sometimes you'll see or just before slipping. Different words. Sometimes you'll see words like max angle before slipping, like what I was just doing a second ago. Or maybe you'll see min. Sometimes the word min is used. Min force to prevent slipping. And there's many other ways this can be phrased, but if you see something in a physics problem where it's talking about being on the verge of slipping, and I argue all of these statements kind of say on the verge of slipping. So let's focus on this one. If you have a problem where it's on the verge of slipping, friction equals mu static times the normal force. Here, this is, oops, mu static, oftentimes called the static coefficient of friction. Again, no units. Look at the units. So far, so good. Both of these cases are fairly straightforward. We have a function and we can plug it in. If we know the normal force from a free body diagram, remember all the work we did last week? We would sometimes, oh, question or no?
Subscript.
Mu static. So that's a subscript S. Yep. Good question. All right, other questions? Still good? All right.
Does little f always stand for friction?
Yes, and to be clear, this is just the notation that I use, okay? Lots of different people. For example, sometimes people use force subscript little f. Like in a textbook, you may see that. You could, yeah, is that good? And then in an effort to reduce the amount of subscripts in the book, what I have tried to do is call normal forces little n's, and then we discussed the subscripts last time. The same idea with our subscripts that we use for little n's, like between 1 and 2, are going to work on our frictions. So I'm going to call friction lowercase f so that I can save the subscripts for between different blocks. Is that good? Yep. Notice this, right? This is crucial. Friction occurs between two things. It's on a surface. So that's why I'm saving that subscript, because it's going to be between blocks 1 and 2, or between 1 and the floor, or et cetera, et cetera. So friction is not a property of an object. These frictional coefficients are not a property of an object. Frictional coefficients are a property of an interface, right? It has to do with a block and what it's sitting on. Cardboard on leather, steel on Chewbacca's fur, whatever you want. Okay, good questions. Should we keep rocking? All right. If you're not in relative motion and not on the verge of slipping, if both of those conditions hold true, F is less than mu static times the normal force. And here is why friction is so diabolical. You've been working for years in math classes, and usually you use equalities. So you're usually pretty good at doing algebra when there's an equal sign. A less than symbol says we don't know exactly what it is from this equation, which basically means if it's not in relative motion, you can't use this equation. Let me be clear. If it's not in relative motion and not on the verge of slipping, we can't use either of these two equations. What happens is students see this equation on test day. They're like, I don't know what to do. I'll just grab it. I don't know. He gave me a distance on this race and a time. I'll just blatantly plug it in as if it's a one-stage problem and hope for the best. I don't know. Whatever. It doesn't work. All right. Let's keep going. Resist the temptation in bold there. Do you see that? Do not use mu static n when it doesn't apply. If you can get that into your head, you'll be all right. Okay? Let me give you an example. In this case, there's friction. There's static friction between the Kim wipes and the block. Otherwise, this box wouldn't accelerate. But it's not even close to being on the verge of slipping. This example, where you have a box sitting on another box, is very commonly when this occurs. Okay? So typically, you'll have some box that's sitting on top. Or imagine you have a box in the back of a flatbed truck, and the truck accelerates, and the box doesn't fall off the truck. That's probably this case as well. All right. So far, so good? All right. Let's see what else we want to do. Oh, yeah. Okay. Let's go over here. Some common screw-ups that students make. Come on. There we go. Okay. These are my pet peeves. In general, N does not equal mg. Just because that was true in one problem you did in high school does not make it true for all of life. It's just not freaking true in general. Sometimes that's true. In general, N is not equal to mg cosine theta. That's not always true either. Students that have drawn an inclined plane problem do this and they're like, oh, N is just either mg or mg cosine. Not necessarily. In general, draw FVD, do force equations, solve for N, the magnitude of the normal force, use in F equals mu static N or F equals mu kinetic N, if appropriate. All right. In general, this strategy, which I'm showing you right here, is like automatic points on test 2. Okay? If you know the different conditions for friction, and you can draw FPDs, and you can write the force equations and solve for the normal force in there. Sometimes the normal force relates to the acceleration, like in an elevator going up. We saw that. Sometimes the normal force relates to a zombie pulling on a string, like a T cosine phi or something like that. All kinds of weird stuff can apply, but this is always true. It's a procedure. You follow it, and then I cannot emphasize this enough. Just because you can get N and shove it into one of these two equations doesn't make it the right thing to do. You always have to check, is it appropriate? How do you know if it's appropriate? Think about the relative motion of the surfaces and the wording of the problem. Did I say it's about to slip? Is it slipping? If it's about to slip, use this. If it is slipping, use that. If either of those two conditions don't apply, how could you get the frictional force? I'll tell you. Do an FPD. Write the force equations. Solve for F. That's how you do it. So in general, if you know this procedure, you can handle friction. I'm not going to tell you it's easy. You got to do a lot of practice to get it right. But once you do the practice, these should be automatic. Okay? Does that make any sense at all? All right. It turns out that, one of the common mistakes, like I said, is students will put in mu for the coefficient. They'll say mu instead of F. And then that makes this last step impossible. That's why I was hammering on that. If you label your frictional force arrows as mu, you can't do this last step. and I write the tests, I know this step is gonna be on the test somewhere. So you gotta get in that habit, right? It's been on every test that I've ever given that I can think of. Probably on the final too, all right? Anyways, let me see if there's anything else. So far, so good? Should we try some problems? All right, so at this point, I'm gonna just start working problems with you. If you feel confident, you know what you're doing, because some of you maybe did a lot of this in high school, and that's fine. Get out your list of problems and start cranking through the whole chapter 6. Let me know when you're done. All right, if you want to work with me, let's all start together. I know I've already mentioned this, but at the bottom of page 99, look at the logic. This is the logic of the Kinwitz problem. Do you see it at the bottom of page 99? We're talking about which way does friction point. I mentioned this because you guys all screwed it up about 10 minutes ago. So make sure you read through that, and this might help you. In particular, you want it, Jules? Thanks, Jules. I'll mention this. Look at page 101. If you look at page 101, it looks intimidating, but I want to be clear, on page 101, you're not doing those problems. You're thinking about how friction would manifest in those problems. Specifically, would it be static, kinetic, or would it be less than, or would it be equal, etc. You're also trying to get the directions of friction. Students are so bad at this, if you go through all of those problems, notice you see the flatbed truck there, you see the 2 blocks there, you see, I don't know, various different options there. That is designed to help you get better at figuring out the directions and which frictional force should apply. Now be careful, some of those statements I deliberately left vague so that they don't make sense. And you have to be like, I can't tell. Sometimes the answer is, I can't tell. So, right, I'm just trying to keep you honest when you're going through there. And I will clarify that in the answers. So when you're reading those problems on page 101, some of them are deliberately left vague, so it's not clear, and you can read the solution and be like, I can't tell. Sometimes that's the right answer. Does that make any sense at all? All right, so do those at home if you want to get good at friction. Let's start simple. Let's start with 6.1. Okay, page 100. I'm going to erase the board. You can start looking at it with your neighbor. 6.1. Dom, anything you want to say about friction? Are those most of the things you tend to talk about, or you don't talk about it? You just assume they know it? Hopefully they do by the time they get to you, right? The most common source of friction is physics instructors, isn't it? Oh, chemistry, that's true. Talk as much as you want. I'll get caught up. That's pretty much the whole lecture for today. Now your problems. Let's see, what do we got here? force applied horizontally. We'll just assume 3 sig figs on all the answers, even though it's a bit sloppy. In lab this week, you'll learn why we only put 1 sig fig on these. Turns out there's a huge variability in these numbers in the real world. We're still going to assume everything's good to 3. So if you wanted to, you can obviously put an extra sig fig on this, so you can put 3 there or whatever. I'm going to be a little bit loosey-goosey with sig figs. All right, what are we supposed to do? At some point, the block will slip. Determine the largest force we can apply without slipping. Any ideas which frictional condition this implies? When you see this, we're trying to get the largest force we can apply without slipping. Those words say something to me. They tell me which frictional condition applies. Which one do you think it is? Do you think it's F equals mu kinetic N, F equals mu static N, or F less than mu static N? Oh, Jules? Oh, whoops. Sorry, I'm on the wrong board too. We're on page 100, sorry. And sorry, I screwed up the board. There we go, page 100, you got it? Okay, cool, thanks, sorry about that. All right, 6.1, all right. Let's go back here. We've got it. What does this sentence tell us? If we can't get this right, we can't get the test questions right, so help me. What do you think it implies? Which one's the second one? Help me.
That equals.
That's correct. Now, you may be saying, wait, it says it's not going to slip, right? But it's also the largest force without slipping. So that must mean it's on the verge. Did that make sense? So notice what I'm saying. Like sometimes the problems don't say it's on the verge of slipping. All right. Anyways, okay, so that's true. I'm going to say this applies. Okay. Whoops, looks like it auto-corrected to draw and FBD. Sorry about that. Let's get the FBD. Somebody tell me one force.
G.
What's that?
MG.
Yep. I'm assuming straight down, right?
Yep.
Somebody else, give me another force. I heard F. What's another one? Normal force. Anything else? Friction. Now let's think it through. Which direction do you think friction is in this problem? The opposite of this capital F. Otherwise, it would slip. Do you agree that friction's got to be going this way? Let me do this. Notice capital letters versus lowercase is going to be pretty important. Capital N means units of force. Lowercase n means normal force. Capital F means the force applied by the zombie. Lowercase f means friction. Check this out. Right angles. Remember I mentioned that normal force and friction are usually at right angles? A good tip to know you're doing the problem right. Okay, what's the acceleration? Why?
Because it's not.
Because it's not slipping in this case. In this problem, if this block doesn't slip, it doesn't move. Therefore, if it's not moving, it's also not accelerating. Be careful. Remember, you could be moving with constant velocity and still have acceleration be zero. So just because you're not moving, but in this particular problem, a block at rest that's not moving is also not accelerating. All right. Okay. How do we do this now? What's the next step if we're trying to learn something here? We've drawn an FED. What do we always do after that?
Right.
Force equations in the X and the Y. Okay, what's the force equation in the X? Somebody else.
capital F.
Equals. Yep, and I'm just going to put this in. Now, to be fair, a lot of us are going to get really lazy in a hurry and not want to write this every time. If you know there's no acceleration, you could just say the rights equal the lefts and the ups equal the downs. So I'm going to do that as well. F equals F. And notice it's critical that we keep track of that uppercase and lowercase. Okay. Y equation, somebody else. N minus mg equals, and do you agree I could just say the ups equal the downs? So N equals mg. How many equations do we have? How many do we have? 3, because we know this extra condition, right? So now let's look at our knowns and unknowns. Well, I got the mass. Do you agree we know G? So we should be able to get the normal force. I've got our coefficient. I should be able to figure out F. Now, do not plug in numbers right away for this problem, right? We want it, right? Just because on test day, you're not always going to have numbers, right? So in this case, why don't we say this is equal to mu static times the normal force. And we say, well, wait a minute, the normal force equals mg. And now look, we've saved ourselves some time. We can tell that the force max without slipping is equal to mu static mg. All right, what's that number going to be? 1 times 9.8 times 0.5 is the famous number, what? 4.9, yeah. Notice, let's check the units. What are the units of mu? None. Kilograms, meters per second squared. The units of mg are the units of newtons. All right. Now, I know this seems silly, and maybe I'm going a little bit slow, but this is kind of crucial to think about. In a lot of problems, this step can help you understand things a lot. What we do is we say, find the value where it's just about to slip. That's our over-under value, right? Think about this. Anything more than this, it will slip. Anything less than this, it won't slip. And why is that useful? Well, now I know if I apply a force bigger than this, the first frictional condition, mu kinetic M, applies. If it's less than this, then I can just say, well, friction is whatever force you apply. Think about it. If you applied 3 newtons of force, 3 is less than 4.9, not going to slip, F equals 3. If I apply 6 newtons, oh crap, it's going to slip. This problem's not valid. Do another FBD where it accelerates and figure it out that way. Is that making any sense? Do you see how annoying friction is? Sometimes you have to do a problem before you can do a problem. That way you can kind of get a feeling for it. All right, enough on that. Should we go to the next part? All right. Whoops. Okay, part B. I may have given away the rest of the problem there. Let's go to part B. I think I could do this right here. Part B. If F is less than, what did I call it? Did I call it F min or whatever? Well, so let's clean up this label. I think in the book I called it F min 2 slip. So F max without slipping. Do you agree that's the same as F min 2 slip? Same kind of words. Does that make any sense? The minimum force to cause it to slip is the same as the maximum force without slipping. I'll just literally write it right here just to make clear. Just trying to get you used to these words, so when you read the problem, you understand what's going on. If F is less than F min, what's the acceleration? 0. What is the frictional force? Let me ask you, if it's not slipping, does this free body diagram still apply? If it's not slipping and it's still at rest, will acceleration still be 0?
Yes.
Yes. So all of this stuff is still true, except for one piece. This last step. This part was only true if that condition applied. However, this is true if A equals 0. So that part is still true. So how could I figure out the frictional force here? What would it be equal to? If you tell me the F, what would little f be? Don't overthink it. If I told you this was 3, what would the frictional force be? 3. So in general, if I tell you capital F, I'm telling you little f for this scenario. That's it. Did that make any sense? Am I losing you? Let me see some thumbs up, thumbs down, just so I know. All right, all right. Is this the right pace or is this too slow? Good enough? Okay. All right. Oh, so in particular, if we set this to 3.00 newtons, we got it. The problem continues on. It says, for example, set F equal to 3. Good? All right. Yes, question.
Is friction tied into the third law of potential?
Does Newton's third law apply to frictional forces?
Or is that why it's like equal?
Well, let me ask you this. What's the force between my hand and the board? There's a couple. What's one of them? Normal force. Which way is that? Perpendicular to the board. What's the other one?
Friction.
Friction, right? So now I'm going to move my hand only in one direction. Hopefully you get this before I run out of board. What direction is the frictional force exerted by my hand on the board? I'm trying to move my hand this way, right? So what direction am I pushing on the board using friction? This way, right? I'm trying to drag the board that way. Think about it this way. If there was no friction, it'd be easier for me to move this way. Agreed? So let's flip it. Which way is the board exerting friction on my hand? As I move this way, which way is the board exerting friction on my hand? Does it want to help me go this way or does it want to oppose that? Yes. By Newton's third law, right? That's the yes. So yes, it does apply. And in particular, it helps us understand conditions like this, where I said, look, the friction that the board exerts on my hand is this way. By Newton's third law, the friction that the hand exerts on the board is the other way. Yes, you are correct. Did that help or make it worse?
Sort of.
Sort of both.
Well, whenever you have a force, there must be two objects. One that's exerting that force and one that force is acting on. So if you are exerting a force on that object, it's exerting you. So no matter what type of force it is,
Could be normal.
friction, gravitational, electrical, magnetic, there's always going to be Newton's third law.
This is going to be not proper language, but I'm going to say it this way because for me, I think it helps. If I normal force on you, you normal force on me. If I friction on you, you friction on me. Now, we don't, that's not right language, but I think that kind of gets the point across, right? So that helps me, even though it's not proper English. I don't say, I'm not frictioning on the board, but you get it, right? If I friction on you, you friction on me the opposite way. Is that helping?
Yeah.
Yeah, I know, it's crazy. I wish there was a more grammatically correct way to get that across, but that works for me. All right, all right. Okay, so part C. Let's get to part C real quick. Good question. Excellent question. Part C. Okay, now we're going to say the force applied is 4.91 newtons. Will the FBD change, or is it going to be identical?
Change.
What's that? I couldn't hear you.
Change because now it's.
What part of the FBD will change? Do I still have a normal force up? An mg down? Do I still have a force capital F this way? Do I still have a frictional force the other way? What changes then? What about it?
The F is equal to the F is equal to.
Okay, this is the part I want to emphasize. The coordinate system over here still have xy. Is a still equal to 0? No, we're able to slip, right? The whole point of doing the first part was saying, look, any force greater than 4.90, this thing's going to slip. If it starts slipping, it's going to accelerate. That's good. What up, Gottlieb? Oh, you want to come teach the class?
Absolutely not.
All right, good. Okay, what's the frictional condition that applies in this case? Is it still the same?
F equals mu k.
Exactly. Now the surfaces are in relative motion. So we can use this. So most of this problem is the same as the previous one, except we can't drop those accelerations to 0. Let's write it out. So in the x direction, what do I get? F minus little f equals max. What's ax in this problem? Is it 0 or is it something? Yeah, so let's call that a. In the y direction, what's the acceleration in the y direction? What's that?
It doesn't change.
Yeah, so in the y direction, can we still say ups equal to downs? Yes. I'll even say why. Because ay equals 0. Ups equal to downs. Did that make sense? Everybody cool with that or not? I know it seems like a little bit of extra cognitive load on you to remember this, but we use it so often, I think you're going to want to learn this, right? The ups equal to downs if ay is 0, the lefts equal to rights if ax equals 0. All right. Well, in this case, we're almost there. I don't know what we're supposed to figure out. What are we supposed to figure out in this problem? What are we supposed to solve in part C? We want F and A. All right. In this case, can I get F? How would we get F? Little f. Yeah, into which equation? Nice. Okay, good. The top one right there. Good. So do you agree we've got everything we needed? We know mu k. Wait, what's n in this problem? mg. We know this. The units checked. In this case, what is it? Is it 4.9? Wasn't it 4.9 last time? Is that still true? No, why not? Yeah, the coefficient. See, that's why we got to watch these subscripts. Mu sub k is only 0.3. M was 1.0 kilograms. E was 9.8. Again, sloppy with the sig figs. I just do that to make Don happy. All right, I got to punch this in, or you guys are faster than me. What you got? 2.94. That sounds about right. What are the units? Newtons, because it's a force. We could do a quick check, right? Isn't this about 10 times 0.3? Shouldn't it be close to 3? Looks good. And those number things. All right. How do we get the acceleration?
You subtract that from big F and divide by mass.
Yeah. Now, I know you could plug this number in, but in this case, I guess since we have all the numbers, couldn't we just stick that in, divide by 1, and get it really quick? Later on, we'll see. It's kind of nice to put in the algebraic result, but in this problem, let's just stick in the numbers and get it over with. So what do we have? We have 4.91 newtons minus 2.94 newtons equals 1.00 kilograms times A. What do you get? Just crank it out real quick.
1.87.
1.87?
97.
97? Okay, anybody else get that? Get a double check too. I'm sure you're right, but I'd rather double check. Put a draw graph. 0.97, you're on it. Thank you. All right. Looking good.
No.
What's that?
The unit.
Oh,
the
the units. Thank you. I screwed up. That should be
meters per second.
absolutely. Good catch. Thank you. All right. Now I want to take this a little bit further. I think, well, I'm a firm believer in graphs, right? So I believe you can learn something by plotting this, and you can see just how odd friction is. In particular, I want to look at the acceleration versus the applied force. Okay, what's the special value of force on the horizontal axis that triggers a change? What's the number? 4.9, about halfway, right? I got the units over here. What is the acceleration for all values less than 4.9? 0, right? What happens when you go to 4.91 to the acceleration?
Goes to almost 2.
It jumps. There's a discontinuity in the graph. This is weird stuff, right? It suddenly jumps up to about 2. And then it's going to go up from there. Can you tell if it's quadratic or linear? If you increase the force linearly, will the acceleration increase linearly or quadratically? What do you think? Does A depend on f to the 1, f squared, f square root, e to the f? Does it? F to the 1, it's linear. It's going to look something like that. This is a weird plot. All right. Now let's look at the frictional force versus F. This is also weird. If you apply 0 force, well, let's put our special number in here, our over under, right? 4.9 is the special value of F. Something weird happens there. If you apply 0 newtons of force, if capital F equals 0, what's the frictional force? 0, right? If I don't push on it, I don't have to push back. If I apply 4.9, what was the value of frictional force?
4.9.
Also 4.9. Probably a little higher. And this is in newtons. This is in newtons, so we got our units. All right. What if I applied 3 newtons? What was the frictional force if we applied 3? 3. If I apply 2 newtons, what is it? So this is a 45-degree angle. Now, what happens to the frictional force if you apply 4.91? What happens to the frictional force? It's about 3, agreed? Now again, my scale might not be perfect. As you apply more and more capital F, what happens to the frictional force? Does the frictional force change? What was that? No. Look at this. Once you exceed this special value, look at the frictional force. It depends on constant, constant, constant. So that means it's on lock here. I think these 2 graphs summarize why friction is so diabolical and difficult. In every problem with friction, there's a transition zone, right? Where above that zone, you're in kinetic friction land. Below that, you're in the inequality land. And we see that the graphs change in this unpredictable way. I don't know if most of you thought this is what you would see when we plotted this. Isn't that interesting though? All right. What do you think? Should we do another problem? All right, let's go. Now I'm probably going to start picking up the speed, right? I went kind of slow played at the first one. All the aspects of frictional problems are in this one. All right. So now at this point, you can just go nuts. You want to try another easy one, a medium one, or a hard one? What do you think? You want to try medium? See how we do? Let's try 6.3 at the bottom of page 100. 6.3. Okay. I'm gonna erase the board. You can talk as much as you want. What's that? Oh, sorry. My bad. Nice job on that problem, everybody. You guys did pretty well. You can tell people like this more than Bratislava running a
I
race.
just pissed off because I felt exact.
We.
I was looking at the answers and I was like. I was wrong.
Still racing on Zoom there, if you're wondering.
Didn't do that one either. And then the rest of it. I just. If I did that, it would be a joke. I think becoming an accountant is so much. Smart. Yeah.
Jules, let's take a lap around and just see how they're doing and kind of, we'll give you a second to get rolling. We're going to loop around the room once and just see. And then I'll do the problem up here later. Obviously, you got the solution if you need it. But see how you're doing. We'll go through the middle. Okay. That's gonna be where to start. Okay. All right. How about up in here? Still good? Get rolling. See. Okay. Over here, you guys still good? Okay, okay. Something that may help over the long term is maybe making those pictures just about that, like double that size. Because what's gonna happen is eventually we're gonna have to label a bunch of crap and it's gonna get crazy. Just let you know, this one should be fine. Instead of making the pictures just a little bit. So what's this for? Pull it. Pull it like that. Oh, pitch. I know that doesn't seem like a big deal now, in the first part. If it's accelerating, sometimes pitch is going to wait, right? Yeah. You got it. Just watch out for that.
What does F min say?
What's that?
What does F min say?
Every problem is a little bit different. In this case, F min is, this one's linked to that one, right? So F min is the minimum, it's the minimum force required to cause slipping. It's that special critical force. You could call it F critical if you want. Good? Yeah, and if you need those extra problems, you could just do that. I want me to break my book over so you can snap a photo of it.
The extra from.
The 6'3.5" and 6'3".
Oh, right. 'Cause I got-
Right, yeah, exactly, because they're the fractional ones that I've added over time.
Oh, yeah, sure.
There may be a couple of those, but. These are on the side of. Yeah, I think that's.
We're not determining a force, but it's determining the mass. So instead of looking at the force, we're looking at mass of the air.
Right, and that mass causing tension, it's really the tension that you accurately depicted. That's correct. You agree that there are some problems where tension doesn't equal G? So what do you say? So it's appropriate that you go G here, not MG. That's the right way to do it. Yeah, good. Question, Maria? What's that? Okay. So good here?
Yeah.
Okay, how about you? Good? Yes. Good. Okay, so FPDs are good. That's the first step. And let's see, what we try to do. Okay, oh, so it's the minimum cost. Which condition applies? Yes, no static layers. What's the acceleration on the version slip? All right, so you said A equals 0, you said that A equals static layer. Cool. Nice job. Okay. Okay. Gotcha. And then I'll give you this critique. One thing you can do is probably make these pictures bigger, but they're meant to be.
The other thing is technically, these aren't FPDs because they're free from the CFD. And so as the problems get more complicated, the benefits of actually drawing the force arrows separate will increase. This problem, there's no real chance to do that. Yeah. But in general, if you're not sure how bad the problem's going to be, draw them about twice as big, and then actually draw the forces on the separate pictures, just so you don't get confused with what's a cable, what's an arrow, and all right, good. Okay, what do you think up here? Getting it done?
I'm just writing out all the equations
Yep.
and then eventually I'll look at it and figure it out.
I almost always do this. Draw FBDs, write force equations, then read the question.
Yeah, that's
Right?
kind of what I'm doing.
Yeah, right. So you just kind of get your, and then the only thing that's tricky is you got to make sure you can tell what the acceleration is before you write the equation. So you got to read enough of the question to verify that. Got it? And sometimes which friction condition applies if you can get that as well.
Oh, yeah, I got this one right here.
All right. What's that? Can I check it? Can you?
You know where the answers are, right?
Oh, yeah.
Yeah, that's why I made all those answers. Because I have no clue. I gotta do the problem to find out the answers. Yeah, so just bring it up. You can get a laptop. You want me to bring you a laptop?
No, I should have brought some.
Yeah, that's the whole point, is so that, right, you don't wait for me to tell you the answer.
Yeah. Yeah, I think you got it. Look, this time you got what, 1, 2, 4. They're sending the equations. What are we trying to find? Oh, okay. So you need to have 2 of them, right? 0 plus tension is not what we want. No, eliminate tension. You can eliminate friction. And you can eliminate molar force. And you got all the terms of mass. It's gotta be. That makes sense. Less than. Well, no, you already did it. Right this. Right. This equation force. Get rid of F using this one. Get rid of G using that. Then. That help? So this equals that. Take this and go to T. Take this over to M. Take this over to F. So far, so good. Okay. That, you got it? Okay. But yeah, you can check your answer. Yeah. Don't forget, you can check your answers. You guys will have to keep that there.
Yeah.
You put the part A. Yeah, do you agree? It's the minimum required to cause slipping. That's a fancy way of saying it's about the same. If it's about the same, it's not slipping yet. Thinking with the wording, right? This is like diabolical. I swear. The right direction. Still making headway? Yeah. Look, that equals this, that equals that, so the other is you're right there,
Yeah, that's it.
You got it. The idea is you got a bunch of equations, right? You get all those equations right, and then you try to eliminate from numbers. Like T squared, friction is a massive. So you're gonna try and rewrite the equations in terms of only known variables. That help you? Yeah. What's that? How would you, well, what are we trying to find? Oh. How could you check it? Yeah, write all the solutions, that way you're not waiting on me. But yeah, because I'd have to do the whole problem to catch up. At this point, you're faster than me. Yeah.
So for B.
Yeah, don't forget, you got those solutions if I'm walking around. And if you finish that problem, keep working on something.
So for B, was this would be, if the mass was the mass minimum. Oh, actually, this is 2, right?
Okay, so if M2 is twice the minimum mass.
If it's gonna start acceleration.
Exactly.
Okay. I was thinking if it said if it was equal to just that M2.
No, M2 is equal to twice. Well, let's just accelerate, so then anywhere you see M2.
Okay, let me see.
Plus 2 times your answer from 3.
Well, I do have a question, which is if it was M2, it was the minimum mass. Like I'm trying to imagine.
So let's say you figured out the minimum mass is like a kilogram
Yeah.
or something. Okay, that gives it, so what I'm saying is, what if you set M2 to 2 kilograms? What should happen?
Yeah.
You were correct, it accelerated. Oh, maybe I don't understand.
Well, what I'm saying is if it was 1 kilogram, I didn't put it on the graph. I figure out like, okay. So we assume the acceleration is 0 because
Remember, acceleration is only 0 if you're at M2 minimum or less, right? Because if you have less than the minimum, it's not going to accelerate.
so then what's the difference between like about to accelerate and being static?
Yeah. So it's in the wording of the question. Is that what we're talking about? So if I say, basically, part A is a fancy way of saying what mass puts this on the conversion slip.
It's okay.
So, right, it's a different way of saying. What
I
is
feel like
the
we've done
mass
this problem
required
before.
on the conversion slip? Like, what is required?
But I can't figure
So
it
when
out.
I say that, that's how you know A is 0. It's on the conversion slip, it's not slipping. What's any more than this, it would slip. Right?
So in that case.
No, I
That's
just
why it's
don't get
okay to
it
say A
anymore.
is
Like,
0.
it's like, you know how you like
So then
something
we
like that?
found out the mass was like
It doesn't
1
come to
ton.
me anymore. So
And we
I'm
go,
like,
what's, oh,
No,
wait,
but
oh,
find out if the minimum mass.
it's a minimum mass.
And so we actually did this in reality. It was on this thing. And now it's just a push. It was an absorption. Cognitive.
It's attached, yeah. Let me show you an example.
So it's a carry.
and then my brain
Yeah.
doesn't
And
work.
I've got an example here right here. I'll show you.
With set of numbers. Like I can't get past that.
That was on the first slip.
Are you ready to do the next part? Do the next part. I can sit here and figure it out.
This is pretty close to being on the verge of slipping. I could tell because any slight bump, flip, right?
Yeah.
Is that what you're
Yeah,
wondering?
that was my question. Like, what's
Yeah.
actual state of it at that?
Yeah. Believe it or not, this is how I broke my bookshelf at home. I should send the school a bill because I was demonstrating this and I had to hit it so hard, I shattered my bookshelf. Not that I'm still bitter. I'm also quite proud of this ladder. I built this one day right before class.
Yeah.
What's that? We'll come back to this one in chapter 12.
I think a lot of you are making pretty good headway on this. I'm going to go ahead and write some stuff up in case you care. But remember, you got the solutions. That's why I wrote them. I killed myself on this chapter writing these solutions so that you'd have lots of nice FPE stuff. Yeah, I think you could learn from it. I hope.
Yeah.
6.3.
One on the previous thing.
Two. Yeah.
So this would be. Time.
So let's take a second to look up here just in case. If you're already deep in another problem, don't listen to me, just keep working. But if you want to, I wanted to mention a couple of things about the FBD really quick. So for me, anytime I see blocks 1 and 2, I like to start getting those subscripts in there, right? Just because that's a good habit, right? I don't want to just say MG, MG. I want to talk about which MG. Now, the tension, I can use the letter T because it's an ideal pulley, ideal strength. We're always going to assume that until otherwise notified. So in this case, same strength, same tension. Chapter 10, that might not be true anymore. We'll worry about that in chapter 10. All right, so in this case, what you could do is you could say, well, I'm looking for, what are we trying to find? M2, right? We're trying to find M2. Well, I look here and I'm like, okay, I know G, but I don't know T. Well, let's try shoving this equation in and see if that helps. So that's going to be F1. Crap, I don't know what F1 is. Well, I can take this equation and plug that in. That's mu static M1. Shoot, I know M. Do I know the mu's in this problem?
No. Yeah.
Yes, it says the table, the coefficients are mu static and mu kinetic. So those coefficients are set in the problem statement. So what are we given? M1, mu static, mu kinetic, and G, I believe, are the nodes. Yes, because M1 is a given. We know the coefficients between M1 and the table. So that's what we've got, and G is a known constant. So these are my givens. Notice the strategy that I have here. I'm figuring out my frictional condition and my FBDs, writing the equations. Then I read the problem and figure out what I'm trying to do again, right? Because it's been so long, I've forgotten. All right, well, wait a minute. Can't I just take this crap right here, plug it in, and I've got it in terms of my givens? So I see M2G is equal to mu static M1G. What drops?
No, gravity. Gravity.
G, not gravity, right? What does this tell us? This would be true on Mars, the moon, or the planet Earth. So somebody come up with the funding to get Jeff Bezos to send us to the moon so we can do this stupid experiment. We need to do this. It's a field trip. See if you can figure, wouldn't that be fun? Doing a block on a Fletcher's trolley on the moon. All right, whatever. Out of all this, it's mu static M1. That's part A. And to be clear, I'm going to now add the subscript min. Why is that true? Because remember, this value of M2 only applies when this one special condition is valid. All right, now I'm going to look at part B really quick, and then we'll take our break. All right, and I know you're tired. Let's just get part B done. And again, if you're already done with it, oh well. it says determine Excel mag if M2 is equal to twice M2 min. This is a common way of phrasing things. Let's be clear, right? What are we trying to find? What symbol are we trying to get? A. Trying to get A when M2 is equal to twice the minimum value. What was that minimum value? Mu static M1. So the idea is you redo the problem and you plug in M2 is equal to twice what we found in the previous part. Let's do it. Are the free body diagrams going to be different? And if so, in what way? There's going to be acceleration now. All right. A lot of times what I'll do is I'll get lazy and just do this, show the acceleration direction. And that becomes my coordinate system. I don't want you to necessarily get in that habit, so let's draw the coordinate system here. Again, I'm using a rotated coordinate system. Follow that pulley. Okay. So now, what do I get in the x direction here? For the forces. T minus F1 equals what? MA? How would I critique myself on this statement? What's that? Well, do you agree AX is equal to A? There's something else that's more glaring that's wrong.
You know which end you're talking about.
Yep, got to clarify which M. I know that seems silly, but I'm going to harp on that every day. Got to get the subscripts right because it's different for the other one. What's the equation for this one?
M2G plus minus T
Equals
M2A.
what could I do to figure out the acceleration? What's the fastest way to do it? Do you remember?
You can like add the equation.
Stack them and add them, right? Let's just put this over here. When you add them, what drops out? The internal force, T. Is T equal to M2G? Absolutely not. Agreed? The most common mistake that I see on the final every year is people get tired and they just say T is mg all the time. I don't know why, but you know this now. Keep that in mind. All right, so what do we get? Hang in there. Break is like 2 minutes away. We're going to get to it, I swear. All right. Shoot. This is F1, isn't it? F1 isn't, no, oh, question.
Shouldn't that be Y on the right?
I rotated my coordinate system here so that I called X down. Do you agree it doesn't matter what you call your coordinate system, as long as you get the arrows right and the signs right? So you could have called this T minus M2G equals M negative A, right? Take a look. I can draw this. So I think what you're saying is this. This is an excellent question and it's important, so we should discuss it. Make that 4 minutes, the break. Sorry. Like,
Sorry, everyone.
no, that's cool. It's right. It's better that we pass tests, right? You could draw it like this, and I think you're saying, couldn't I just draw X and Y like this, right? Now it's critical that we talk about A as the magnitude, and now we don't really get to choose this, right? We know this block is going to accelerate that way with magnitude A. If I'm going to use the symbol A here, that's the magnitude, the direction's down. What would this free body diagram equation look like in the Y? What's the force equation here? T minus M2G equals M2 negative A, right? Because A is opposite the coordinate, and nobody remembers this negative sign, and then they miss their test, and then they have to retake and deal with me another semester. Not what we want. Look at this. In here, A and MG should have the same sign. Over here, in my rotated coordinate, same sign. Do you agree? Basically, rotating the coordinate system helps me prevent forgetting this minus sign. That's why I do it. Does that make sense? It's not that it's the right way. Both of these are absolutely correct. However, historically, students forget this minus sign all the time. That's why I like to just say, good? All right. All right. Shoot. What's F1? What is it?
Mu S and one.
Mu N1? That's not good enough. There's two mu's. Which mu?
That's a mu S.
Oh, mu S?
You started.
That's wrong. It's accelerating now. It's sliding relative. Do you agree? So watch out. So we see there's two things that change. The frictional force equation, now that it's moving, it's slipping. Use F equals, whoops, mu kinetic, right? So there's an acceleration now, and the friction type changes. So there's a subtle difference there. But in here, this is mu kinetic. Do I know the normal force? 1. I could do an FBD here. Oh, I did. What's the forces in the y direction?
N1 minus M1G.
And do you agree because AY equals 0, ups equal downs, right? Looking pretty good here. Let's rewrite because it's getting messy. M2G minus mu kinetic M1G equals M1 plus M2 times A. What is M2 for this problem? So we got to plug that in. And now we see the final result is going to have only known constants in it. U static is known, M1 is known, G is known, U kinetic is known, et cetera, et cetera, et cetera. Got it? You want me to finish it out? Just for the heck of it? Or if you're fishing for the hell of it? Okay. What can I factor out of every term? Well, I'm going to rewrite this side real quick. This looks like M1 times 1 plus 2 mu static over here. Agreed? Over here, ugh, I don't know, it's going to be a mess, but I guess I got to rewrite 2 mu static M1. There's a G. I can factor out a G. Oh, I could have factored out an M1 as well. Do you see that? There's a G I pulled out. I guess I could pull out an M1 as well. I'm just factoring this side out. I pull out an M1G. I'm left with 2 mu static minus mu kinetic. And then on this side, I could divide by M1 times 1 plus 2 mu static. And this is all equal to A. The M1's dropped. We see that the units check. No units, no units, no units, no units. G has the right units. I could rewrite this to make it look pretty. Something with the correct units times something with no units. Got it? Go ahead and take that break. Woo! That's a lot of mu. Just algebra.
You didn't make a Mewtwo joke.
What's that?
You didn't make a Mewtwo joke.
I'll work on that. I'll work on that.
All right. Oof. All right, where are we here? Okay, so at this point, where are we here? Well, we've done quite a bit. Let's look at 6.14 really quick. Okay, 6.14.
What should I do right now?
Okay, a quick visual on this, and actually this relates to some of the stuff we're doing in lab here. Going to use our trusty book and box. The idea is right now, these Kim wipes are sitting on there. As I angle this, I keep increasing this. Then at some point, the Kim wipes begin to slide. So there's some angle at which these Kim wipes slip. That special angle is called the critical angle. Then increase the angle until the block is on the verge of slipping. At that point, what frictional condition holds?
F equals mu s n.
That's right. It's on the verge of slipping, mu static end. All right. If you wanted to analyze this problem, forget the question. If you wanted to learn about this scenario, what's something you could do? Free body diagram, right? We could, right? If we want to learn about this system, we could probably draw an FBD. Which way is the normal force? Show me with your hands. Perpendicular, okay. Which way is mg? Straight down. In this problem, as you raise this up, which way is the frictional force? Up the ramp. Notice it's going to be right angles again. Okay, frictional force, there we go. If you had to choose a coordinate system, would you want to use a regular straight up and down or rotated? And if so, why would you choose one over the other? Why would you choose a rotated coordinate system?
So then you can have friction on the x-axis, on one of the axes.
What else? Normal force. So notice in this case, by rotating it, two of the forces line up. We only have to do SOHCAHTOA on one of them. Ah, so there is a purpose to that stupidity. Okay, that's cool. All right. Are you happy if I split this mg up like this? Everybody cool with that? I'm not. That's totally wrong. Is this component aligned with the x-axis?
No.
No, that's totally wrong. The hypotenuse should always be the original vector. Look, this was the hypotenuse. That would, you totally get it wrong. That is splitting it up. You see the difference? Don't ever forget that. It's tricky. You get lazy, you're used to drawing right triangles. You drew a right triangle, you're like, oh, that looks pretty good. Now, help me out here. Let's go through this again. If this angle is theta, what's this angle right here? 90 minus theta. What's left for this little angle? Theta. These two add up to 90, just like these two add up to 90, right? A triangle has 180. This takes 90 of it, so there's 90 between these two angles. This is a right angle. There's 90 between these two. So that helps me see this is theta. And in this particular problem, it's theta critical. I'm going to label that. Notice in this case, opposite down here. What are we trying to do now? At this point, let's read. What are we trying to figure out? Oh, sketch an FBD, figure out the coefficient. So we're trying to find the frictional coefficient. What thing are we looking for? If we're looking, what symbol am I looking for? Mu. That's the frictional coefficient. All right. What's the sum of forces in the y direction here? Oh, what's the acceleration for this problem? Should be 0 because it's on the verge of slipping. So somebody else might draw up the plane positive, somebody else might draw down the plane. We know that shouldn't matter. But what's true for the forces in the y direction in this problem? What's the force equation? Yeah. Somebody else. What's the force equation in the y? Normal. We can just say ups equal downs, right?
Plus mg.
Yep. In the x direction, somebody else. Other than those two. What about it? Sorry, it's hard for me to hear.
There's acceleration 0, so it's equal.
Correct. Absolutely. Beautiful. What are we trying to find? The coefficient. Remembering what we're trying to find is actually useful. Any ideas how we might approach this? What could you do?
Plug in US.
Yeah, we could plug in USN here. What would Horatio do?
Take a ratio.
Take a ratio. Look, I'm going to line this up another way. If I take a ratio of this, what drops out on this side?
mg.
What drops out on this side?
And
And that Horatio is pretty clever. What's left?
tangent.
Isn't that crazy? Wait, what about the units? Shouldn't this have units of newtons?
No.
No, it's a coefficient. It's unitless. Tangent, unitless. This is a classic way to figure out the coefficient of friction in a problem. You could take an incline, right, and make it of one material, and you can put a block on it of the other material. Because remember, coefficients depend on both materials, both objects. Right? So you can take these two materials, make a ramp out of one, put a box on it, and then you just raise it up. And then at whatever angle it slips, you punch in the numbers you got. Kind of cool. So if you're wondering how you can figure out these coefficients in real life, we'll probably be doing something like this in lab with a little bit more complicated problems. In lab tomorrow, what I'm going to try to do is make everybody have to do some kind of force diagrams with two blocks, right? And so that you have to do these types of systems of equations. And then there'll be, some of them are angled up the hill, some of them are angled down the hill. Sometimes they'll be, I don't know, we'll see. There's a bunch of different options for which way you're drawing FBDs, but they look basically like homework problems. So we'll basically be doing these complicated sets of equations, solving for a coefficient of friction, or just like we did in the last problem, remember where we found the minimum mass? You could do a problem like that in lab, right? So basically, I'll either tell you the coefficient and you solve for the masses and then do the experiment, or I'll give you some complicated situation and you solve for these coefficients, or do both. All right. Feeling good? Now, at some point, you're going to be pretty good at algebra, right? Hopefully that point is now. I've got so many problems in this chapter. One of the things that students screw up all the time, what's the hardest part in doing all these problems, do you think? if you were doing these problems over and over again, what's the part that you need the most practice at?
Identifying all the parts.
Identifying the parts, what equations to use, FBDs, and these. After that, it's all algebra. To be fair, most of you need some work on your algebra. I did see your tests. All right, so it's not like doing the algebra, but at some point when your algebra gets so good, all you really need to do in these homework problems is set them up. Can you get the FBDs right and the conditions right? At that point, trust that you can do algebra. Once you've done a few of these problems and get the algebra tricks down, start flying through them and doing the FBDs and the equations. Got it? Ready for a hard one? Let's try 6.21. All right, 6.21. Got a zombie, a block. That is the zombie's neck. The zombie's arm still off. Oh, let's. Okay. Now, is this even possible? Is it possible to pull a sled by pulling on a block that's sitting on top of it, or is that? Let's take a look here, right? I could give you an example. Imagine this is the sled. This is the object that's on top of it. Hopefully I could get this. Oh, no, there's not enough friction here. All right, so in this particular case, or there, I guess there's too much friction between the ground. Let's try another example.
What
Let's see.
about with those paper towels?
How about with this? Let's see if we can do it with this. Oh, there we go. Got it? So we see that the sled is being pulled along by the book that's on top of it. So this can happen in the real world. Now this is pretty hard to do, actually. To be clear, the coefficient of friction between the sled and the ground needs to be very low. Well, this is very smooth, and this surface is also very smooth. So we do have negligible friction between the sled, or this paper, and the ground, right? And then there's non-negligible friction between the book and the sled. Got it? All right, let's go back to it. So it is possible, but it does have to be kind of an unusual situation. Know that this thing has mass m, this thing has mass 2m, this thing has mass 4m. What else are we told? Yeah, I'm just going to put this up. Box does not slide. Box does not slide relative to the sled. No friction between, let's say, negligible friction between ground and sled. That's another fact. Oh, I see. That's what you were saying. The zombie accelerates. Yeah, that's what we got. Okay. All right. We were trying to learn about this. What would you do? FBD of what? Of the box, okay? Give me one force on the box.
The tension in the air.
Okay, tension. We know that tension? No, but we do know this angle down here, right? We know that theta equals 30 degrees. Okay. What else?
Gravity. MG.
mg. So remember, it's okay to call the force gravity. So that's correct. We don't want to call it G gravity. Now, wait a minute. What's wrong with this? This is a different style. What mass is the box?
2.
So what should I use for mg? 2 mg. Don't overthink it. So in this one, we don't need subscripts because we're just going to call the mass 2m. What else? Normal force? What's a good name for this normal force? I'm going to call it 1, 2 because it's not on the ground. You agree the ground is down here? So this is a normal force between the two blocks. Maybe even to highlight that, I'll draw it in blue. Figure not to scale. Anything else?
F1.
F12. Which way? Why?
No, to the right.
Well, let's think. If there was no friction between here, which way would the block move relative to the sled? Again, pretend there's no friction. Which way would the block move relative to the sled? Friction points opposite the relative motion. This block is trying to go that way relative to the sled. The sled is holding it back. Do you agree? You were right the first time. What's a good name for this friction? Friction 1, 2, because it's between the two blocks. Right? The sled is trying to hold back the block. That helps me. Okay, the sled frictions to the left. Anything else on this one? I think that's it, right? Okay. What's another good FBD we could do? Sled. Okay, somebody else. Give me a sec. What's one force acting on the sled? Somebody else. Wait, what should I draw for that? mg, excellent. What else? Is the tension acting on the sled? No, it's not directly acting, okay. The normal force between them pushing which way? Exactly. Look, the sled pushes up on the block with normal force 1, 2. Therefore, the block pushes down on the sled with normal force 1, 2. What else? The friction. Now I know saying the word friction is not good. Which way do you think the friction points? Yes, exactly. The sled frictions on the box this way. Again, apologies for saying it that way. So the box frictions on the sled this way. And again, frictions is not a verb. Sorry, my bad. I think it helps. Right? Friction acts this way on the block. By Newton's third law, that way. That's what you were asking earlier, right? Anything else? Why is there another friction? You agree that you're right? There could be another, but this particular problem says we don't have to worry about friction between the ground and the sled. Otherwise, there'd be another friction. From what? Yeah, so what do you think I would call that? Okay, you could call it N. We could also call it N1. Either way, that's fine. In this case, I don't know which I use, so we'll just call it N. Anything else? What's the force going to the left? That doesn't have to be one, does there? Remember that other problem? Okay. Couldn't I just change this to M2 or 2mg right here? No! Think about it. The zombie's pulling up on this block. This is the most common mistake people make. Normal force is not right. Think about it. The zombie's lifting up on this block, so this normal force is only part of 2mg. In particular, see that? Isn't that tricky? Now you know why we're doing it. In this problem, we see that 2mg equals n12 plus t sine theta. If you're pulling on something with a rope at an angle, you're helping to support it so it's not all on the table or the sled or the box or whatever. Isn't that tricky? Just watch out for that. If you got a rope at an angle, usually there's some component of tension helping support the weight. Enough on that? Sneaky. Is this thing accelerating? Which way? Exactly. The zombie is connected to this thing. So the zombie, we didn't even need to draw a free body diagram for the zombie. The zombie is useful though, because if the zombie's accelerating and this thing's tied to it, get out of the way. At this point, what could we do next? Oh, yeah, but I mean, we draw some FEDs. What's the next thing that we generally do? Force equations, and then reread the question. What are we looking for? I don't even know what we're looking for.
I was gonna say with the question.
Yep, read the question. Exactly. So at some point, where do we get it? We basically, when we're starting to do these problems, you get an FED on the page, you reread the question, you find out what you're looking for, you maybe write some equations, turn the crank. You want to try another one? I think we should do another one, and you guys should finish this at home, because at this point, it's all algebra. Agreed? The hard parts here, let's review. The hard parts here are, number one, remembering that N12 is not always going to be the mass of the block times G. That was a key error. The other one was getting these frictions correct. Is there another FBD you could draw here? We could do the zombie. Is there another one?
Oh, is it the system?
The system. That's something else we should mention. Sometimes that's useful. Does this apply? Are these objects moving together as a single unit? Yes, because they're not moving relative to each other, that's what allows us to treat them as a system. You can't just take any two random blocks and treat them as a system, but if they're moving together in unison, then we can do that. Let's do that. What's one force? Tension? What do I have going down? What's the weight? 3 mg, because it's m plus 2m. Is there a normal force up? Yeah, exactly. What did we call that? Absolutely. What about these internal forces? Do I know the acceleration? G/5. Right. Which equation or which FED is the easiest for determining the acceleration? Is it 1, 2, or system? Which one is going to be the easiest for figuring out acceleration? Probably the system. But if we need it, we could come over here and grab this one or that one as well. Now in this case, oh, wait a minute. We already know the acceleration, don't we? I apologize. We're supposed to be figuring out the tension in this problem. I misspoke. Which one is going to be the easiest for figuring out the tension? This one. You agree? You can see it right now. T cosine theta equals what? Let's write the force equation here. This is theta. If I'm doing this in the x direction,
Cosine theta equals
not quite. What mass? 3m. Because I have to use the total mass, and I was just making sure you got that. Maybe you knew that, I don't know. Wait, we're done. We know theta, we know 3, we know 5, we know g. We got it. And was it given? Piece of cake.
we only know one component of the acceleration.
Well, we know ay is equal to 0, right? Because right, if the zombies accelerate, the zombie's walking this way on the ice. So the zombie, right? I'm assuming the zombie doesn't have a jetpack. But if it did, that would make it a lot harder, agree? So I'm assuming that's kind of a default. We're assuming it's just accelerating to the right, which seems reasonable. Most zombies do. Yeah. And then so after you get this, once you know T, do you agree you can come over here and figure out F12? We know N12, we can figure out that as well. Like you can figure out what fraction of the weight is supported by the sled versus the tension. The trick in almost all of these is, can you get that first thing? And so remember this extra trick. You can draw 1, 2, and sometimes the system makes life a little easier. If you don't remember the system, you can always stack the equations, add them, the internal forces drop out, right? You remember what I'm saying? Take a look at 6.17. That's a pretty good one. If you have trouble, you could do 6.18 and a half first. 6.16 is a pretty good one. 6.19 is a good one. Oh my God, they're all good. Look at 6.24. Look at 6.22. Look at all of them. I love 6.25. Oh, look at 6.30 on the top of page 107. What if you're pushing stuff all across the ceiling, right? These are all interesting. 6.33 is a really weird one. In that case, when you release them from rest, the two blocks do not move in unison. So I gave that as a test question, I don't know, 10 years ago. And for some reason, people tried to draw a system diagram on that, but one block's going down and one block's going up. It's goofy. You can't treat them as a friction. You can't treat them as a system. In particular, that's a weird one because, again, I'm talking about 6.33. The friction in that problem ends up counting double because it's working against the block going down and against the block going up. With the new, yeah, so that's a really weird one if you're, I don't know, into it. Oh my gosh. Look at page 109, in particular, 6.37. It's a critical problem. You like that? If you're holding 3 books, crap, more crap, and chemistry. Or like 6.39, remember we talked about the truck? If you're interested about how fast could you accelerate in the truck without the box falling off the back? You could do that problem. Oh my gosh, 6.35 is crazy as well. All right, anyways. All right, so I'm gonna go ahead and give the test back now. That's it for friction. We start up circular motion.
I'm not gonna look at it.
just
I'm
be
gonna look at
aware.
it in my car.
Be aware of the following. A lot of students typically are kind of like, oh, I've seen this in high school and they feel pretty good. This is about the time where it starts to be like, oh, I need to be working hard. So just be aware, the difficulty level is going to slowly, it's going to increase. I won't say slowly, but not say rapidly. Here's the test. So I want you to be realistic. And in particular, I want you to think about the following. In lab, we have 2 more oral presentations. Okay, it's basically 3-week cycles. We do an oral presentation, then a review for the next exam. Then we've got a couple coding labs sprinkled in there, right? So basically what we've done up to till now, we do it twice more, right? We've done a little coding and then a presentation. We'll do a presentation and then a study day, and then a coding, some presentation and a study day, etc. And then some more coding at the end. So that's what you've got in lab. If you're not going to pass the course, don't waste your time on those labs. Focus on your other classes where you still have a chance. Okay? And this is graded out of 31. Don't ask me what it's graded out of. It's graded out of 31. All right? So it was brutal. The solutions. Don't ask me how to solve them until you've read the solutions. I have no problems going over it with you, but I write the solutions for you so that you can look at them at home, find out what you don't know, and then ask. So don't ask me how to solve these problems until you've looked at the solutions. I will help you at that point, definitely. Okay, go nuts.
You want to?
They're kind of in alphabetical order, but I know some people have more than one last name, and I might have accidentally alphabetized them by the wrong name, and I apologize for that. I'm running out of room here. I think the top grade was like a 94. There were no Bs. No Bs. It was a very weird grade distribution.
There's no way.
If the score is 10 or lower, it's just not going to happen, right? Because this was the easy test. You're out. You're welcome to get out of here. You're welcome to use the computers and look at the solutions. I'm in office hours now, so if you want to look at the solutions and go over it. But yeah. If you're in that 10 to 14 range, that's trouble. If you're 14 or over, you're probably going to make it happen. But you definitely have to keep working, all right? If it helps you feel better, I didn't pass my first physics class either. Michael, you'll just get it in lab tomorrow. You don't have to worry, though. I'll say it that way.